let's look into nth order ODEs. Let's look at nth order linear ODEs. So for second order, we had the format p times second derivative of y plus q first derivative of y plus r y equals the non-homogeneous term. For order n, the structure is very similar, except we have more terms. So we start categorizing it. Instead of using one different letter for each, we call it all p, and we start by p0 that is matched with the nth derivative of y, plus p1 that is matched with the n minus 1th derivative of y, down to pn minus 1 that is matched with the first derivative of y, plus pny equals g. We expect p1, p2, p3 up to pn and the forcing term g to be continuous real functions on an interval between alpha and beta for t. We also want p0 to be different than 0 for all values of t in that same interval. And as we have done previously, we can write the nth order linear differential operator. And this has the form as we expect, that is nth derivative of y plus p1 divided p0 and n minus 1th derivative of y plus all the other derivatives. We have just divided the previous formula by p0, and we call this a linear differential operator because we interpret it as taking as input y and spitting out a new function. And we want that new function to be equal to g divided p0. Contrary to second order ODEs, nth order ODEs require n initial conditions. So for second order, we only require two initial conditions, a condition on y and a condition on y prime. For nth order ODEs, we require a condition for all derivatives up to n minus 1th. Think of it as the idea that now you're integrating n times. And for the solution to be unique, when you integrate n times, you need n extra conditions. And you can choose the point in which you assigned the initial conditions as any t0 within the interval I of continuity of your functions. And we have a theorem, as we did for the second order ODE, that states that if everything is continuous on an interval I, there exists a unique solution. And that solution can satisfy all initial conditions, and it exists for all times t in the interval I. So if we have continuity of p0, p1, p2 down to pn and g, we have existence and uniqueness of solution in the same interval in which we have continuity. In the homogeneous case, we'll see that it's very similar to the homogeneous case in the second order ODEs. In particular, if in the homogeneous case we have two solutions, then any linear combination of these two solutions is also a solution. Can we write all solutions as linear combinations of base solutions? And how many base solutions do we need? So assuming that it is as in second order, in which we can write all solutions as sums of base solutions, how many base solutions are there? Well, imagine that you have yn to yn different base solutions. Are they enough? Well, you want them to satisfy n equations given by the n initial conditions. So you want to find a combination of c1 y1 plus c2 y2 down to cm ym, such that the first derivative matched your initial condition, their zeroth derivative, their nth derivative, all matches the initial conditions that you had imposed at t0. Those are n equations. If you want a uniqueness result, the only situation in which we can hope for one is when the number of base solutions is equal to the number of to the order of the ODE that we want to solve. On top of that, we also need that the determinant of the coefficients of the algebraic equations that we have written is different than 0. This determinant here is called the Vronskin. So we are building something very similar as what we built in 2D. In the case of second order ODEs, we only had y1, y2, y1 prime, y2 prime. Now we have a much bigger determinant. But it's in the same format as before, in the sense that it takes y1, y2 down to yn, and the first line of the matrix is y1, y2 down to yn, the second is the first derivative, and then you go to the n minus first derivative. And as it holds for second order ODEs, the Vronskin at t0 is different than 0 if and only if it is different than 0 at any point in I. So we have this interval of continuity, and we can check any point in that interval to decide if the Vronskin is different than 0 or not. So now we have this important theorem. If P1 to Pn are continuous on an interval I, if y1 to yn are solutions of the linear differential operators, and if the Vronskin of the solutions we just found is different than 0 for at least one value in the interval we just defined, then any solution of our nth order linear differential operator equal to 0, it can be represented as a linear combination of y1, y2 down to yn. This is a very strong statement. It means that when we're going to nth order ODEs, we can do the same thing as we did for second order ODEs. We find n different solutions, and we use that to combine them in any solution. As for second order ODE, y1, y2 to yn is called a fundamental set of solutions. Let's look a little bit at linear dependence or linear independence. The very general definition of linearly independent elements is that you look at A1, A2, A3 down to AN, all the same type of elements, and we call them linearly independent if C1 times A1 plus C2 times A2 plus C3 times A3 plus Cn times An is equal to 0 only if you're setting C1, C2, C3 down to Cn all equal to 0. Notice how 0 in this case has to have the appropriate form. We're going to have to make some examples to see where we can use this. We are assuming C1 to Cn to be real valued. And we can apply this definition of linearly independent to a lot of things, actually. We can call vectors linearly independent. We can call polynomials linearly independent. In general, we can talk functions to be linearly independent. And that is the topic we are the most interested in now. When are functions linearly independent? When this request is satisfied. Let's check an example. We take three vectors, so vectors of 3 elements. We call A1, 1, 2, 3. We call A2, 1, 0, 1. We call A3, 0, 1, 0. Are they linearly independent? We check. Can we find C1 plus C2 and C3 such that C1A1 plus C2A2 plus C3A3 is equal to 0? In this case, 0 needs to be a vector of zeros of the same length of the vectors we had. So we try to cancel the elements of the first vector. We take C2 to be minus C1, so the first ones cancel out. We take C3 to be minus 2C1, so we cancel the second element, but the third element still go through. So in order for this to work, we need C1 equal to 0, that gives C2 equal to 0, that gives C3 equal to 0. So yes, they're linearly independent. Let's look at another example. A1 is equal to cos t, and A2 is equal to sin t. Here we also need to say on which interval t is taken. So here we're taking the interval 0 to 1. Are they linearly independent? So we need c1 cos t plus c2 sin t equal to 0 for every t between 0 and 1. So we need c1 equal to 0 and c2 equal to 0. So yes, they're linearly independent. Let's look at a more complicated case in which we don't know immediately the answer. We have f1 of t is equal to the constant function 1, f2 of t is the exponential of t, and f3 of t is t times the exponential of t. And we're looking for t between -3 and +3. Are they linearly independent? Well, we need to check if we can find c1, c2, and c3 different than 0, or do they have to be equal to 0, such that their sum is equal to 0. And it must be true for any t between -3 and 3. Well, if it must be true for any t between -3 and 3, maybe I can choose some values. Look at that it works only in one direction, not in both. If picking 3 values, then I can prove that they're linearly independent, it works. But if I choose poorly the 3 values, I might have that I can prove linearly dependency, but because I chose the 3 values poorly. Think if you choose t to be the same value 3 times, that doesn't give you information. Anyway, we choose t equals to -1, t equal to 0, and t equals to 1. And we try to solve this 3 equations at the same time. Notice that this is equivalent to say that we have 3 vectors, one being 1e minus e, then the other one being 1, 1, 0, and the third one being 1e. Are they linearly independent? And if you do the calculations, well, one equation just tells you that c1 is equal to minus c2. You can plug that in, and you find 2 solutions for c2 as c3 multiplied by something, and each one is different. So they can both be satisfied only if c3 is equal to 0. So c2 must be equal to 0, so c1 must be equal to 0. So yes, 1 exponential of t and t exponential of t on the interval -3 to 3 are linearly independent. We now have a theorem that makes our job quite easier. If we take functions f1 to fn continuous on an interval I, they are linearly independent if and only if their Wronskian is non-zero for some value of t in that interval. That makes our job so much easier. It changes from let's try to find the right places in which we can compute things to just setting a formula for the Wronskian and trying to find if it is non-zero for some values. And we conclude by saying that if y1 to yn is a fundamental set of solutions, if and only if they are linearly independent solutions. So we can go through that in 2 different ways. We can either try to find linearly independent solutions and then we construct a fundamental set, or we can try to find things that fit the Wronskian properly, and then we know that they're linearly independent. What happens in the non-homogeneous case? So in this case, we have a right-hand side that is g depending on t, where L is the n-order linear differential operator we introduced earlier. It works in a similar way as how it worked in 2 dimensions. If we have 2 solutions of the non-homogeneous ODE, then their difference is a solution of the homogeneous problem. And we can prove that by linearity of the differential operator. So the differential operator applied to y1 minus y2 is equal to the differential operator applied to y1 minus the differential operator applied to y2. That is g of t minus g of t, that is equal to 0. So as we had for the second order ODEs, we have for any order the fact that the general solution of the non-homogeneous case can be written as a sum of the homogeneous solution plus a particular solution.